distribution of charge, and here second is the continuous distribution of charges. And continuous distribution of charge in the pattern, it is the like this: charge is arranged to the length L uniformly with the linear charge density, that is the lambda, and at any point P we will calculate the relation for very short, very small charges, infinitely small charges, that is the dq. So we have a relation or the force at this point P on the charge q naught, that force, and that force we will write here according to the principle of superposition. According to the principle of superposition, according to principle of superposition, that force vector is equal to, here it is q naught by 4 pi epsilon naught integration of the whole length L, and for this it is the lambda dl by the position which we will consider from the origin. From the origin, let it be the origin, that is the y, x, and here it is the z. So the point up to this is the r dash vector, and up to the p point it is the r vector. So the relation we have, the distance from here is the r vector minus r1 vector. We write here, that is the magnitude of r vector minus that r1 vector whole cube to that of the r vector minus r1 vector. And this is the equation number 1. And thus next we will use the definition of the electric field. Since electric field E is represented as limit q naught tends to 0 for what? The force to that of the discharge q naught. Force we have in the equation number 1. So that is the electric field E vector is equal to limit q naught tends to 0 by 1 by q naught into force. In place of this we have the q naught here, q naught by 4 pi epsilon naught, and integration of the to the length L, integration to the length L, that is lambda dl by r vector minus r1 vector whole cube to the r vector minus r1 vector. Now q naught is cancelled, so electric field due to the linear charge distribution, we write here the continuous distribution. Number 1 is the linear charge distribution. At this condition, we have the electric field E vector is equal to, that is 1 by 4 pi epsilon naught integration to the length lambda dl by r vector minus r1 vector whole cube to the r vector minus r1 vector. And this is the electric field due to the linear charge distribution, and this is the equation number, let it be the equation 2, here it is the equation 3. So first we observe the arrangement is linear charge distribution. Now we will see the next one, B second, for the surface charge distribution. For surface charge distribution, just we change here is the B second, surface charge distribution. Now here again, according to the principle of superposition, the force we will write. Now the arrangement is surface charge, so we make a surface here, and that is the, suppose this is the surface at which very small surface element ds, where the charges are distributed uniformly continuously with the surface linear charge density is the sigma, and the location for this is the R1 and the point P where the test charge we consider, that is the force F vector. Again, the distance from this small ds length element containing the dq charge is the distance is r vector minus r1 vector. So for that relation we just change the simple way where we have taken earlier the lambda or dl. In this place we will write the sigma and ds. All the same, everything is the same. The process is also the same definition we will use for the electric field. But the arrangement, little the change is here. We consider the surface charge density to that of the small surface element ds. And everything is the same. In place of the integration of length, we write the surface s. Here also the s. Here also the sigma ds, and for the surface integral of s. And likewise, the third is the volume charge distribution. Third, the same way we will do the volume charge distribution. Let's suppose here is the volume, and we consider the very small volume element. Suppose it is such type of volume where we consider the volume element like this, the volume element. Suppose, and the position for this volume element is the R1. R1 is the position vector for this, where the uniform charge distribution is up to this volume, that charge is uniformly distributed with the volume density. Volume density is the rho, and the position from this volume density to that of the point is the point P is the R minus R1, as similar one as we have used in the earlier cases. The same character, by very little change is here, and that change is the in place of density we will write the rho, in place of the surface we will write the volume, and here the integration of the volume, that becomes the force, superposition of this. Now in place of this we change it here, number C, volume charge distribution, and that becomes the equation 1, and with the same formula we will use to find the electric field, but what change are done in the earlier, that will be in the second step also, that is rho dV here to the volume, complete volume, integration of complete volume, and we find the electric field rho dV by the integration of the complete volume P. So in this way we calculate, we have seen the electric field, and that is the process known as the superposition of the electric field, or principle of superposition of electric field. In the two ways we have studied, one is the discrete distribution and another is the continuous distribution. How we calculate, we come to know, and with the better understanding, in the next step we see the another factor of the charge with the electric field. Thank you.